The trillion-dollar semiconductor industry is staring at a total collapse. By leveraging cryogenically cooled qubits, we've bypassed the binary constraints that define modern computing. Every data center and processor factory currently in operation is now architecturally obsolete. We aren't just shifting gears. We are witnessing the extinction of traditional hardware. So, how exactly will quantum compute chips achieve this unprecedented disruption? And what does this mean for the future of computing as we know it? This isn't just about faster computers. It's a fundamental change in how we solve the world's most complex problems, from discovering new medicines to breaking every code on the planet. By the end of this video, you will understand why the age of silicon is ending. Before we dive in, let's understand the core problem. Imagine a massive library with 1 billion books. A classical computer, even the fastest supercomputer, must check each book one by one to find a specific sentence. It's fast, but it's sequential. A quantum computer, however, operates on entirely different principles. It can, in a sense, read every single book in the library simultaneously. This isn't magic, it's a new kind of physics. Let's break down how this leap is possible. First, we must understand why classical computing has hit a dead end. Companies like NVIDIA have mastered shrinking transistors down to the nanometer scale, but with architectures like the H200 and Blackwell, they've hit a thermal wall. Packing more transistors closer together generates immense heat, and the performance gains have begun to flatline. You get diminishing returns. Quantum bits, or qubits, don't have this problem. Their power doesn't come from density, but from their quantum state. This allows for a scaling potential that physical silicon simply cannot match. But heat isn't even the biggest flaw. The fundamental architecture of every modern computer, from your phone to a supercomputer, is inefficient by design. This is the von Neumann bottleneck. The processor and the memory are physically separate. Data has to travel between them, creating a traffic jam. In modern AI clusters, this bottleneck is so severe that the multi-million-dollar GPUs can sit idle up to 90% of the time, just waiting for data. A quantum chip obliterates this problem. Thanks to a property called superposition, a single qubit can exist in a combination of both 0 and 1. A quantum computer, therefore, holds the question and all possible answers within its very structure, all at once. There is no travel time. To maintain this fragile quantum state, you need an entirely new kind of infrastructure. Forget the loud, hot server racks of a traditional data center. This is a dilution refrigerator. It cools the quantum core to temperatures colder than deep space, just fractions of a degree above absolute zero. And forget copper traces on a motherboard. Instructions are sent to the qubits via gold-plated microwave waveguides, ensuring a perfectly clean signal. This isn't science fiction. These machines are already being used today. And what are they being used for? To solve problems that are impossible for silicon. The most famous example is Shor's algorithm. Most of the world's encryption, the very thing that protects your bank account and government secrets, relies on the fact that it would take a classical supercomputer trillions of years to crack it. A sufficiently powerful quantum computer running Shor's algorithm could do it in under 30 seconds. And with recent breakthroughs in room temperature photonic bridges, these quantum cores can finally interface with our existing fiber optic networks, making their power accessible. This makes any system relying on traditional silicon a legacy liability. Now, despite this power, it's crucial to clear up some myths. Quantum computers will not replace your laptop for writing emails or browsing the web. They are specialized machines for specific types of complex calculations. Second, they aren't just faster classical computers. They operate on probability. They run a problem thousands of times to find the most likely correct answer, a fundamentally different approach. And here's the mind-blow moment. A quantum computer isn't a perfect deterministic machine. It's a fuzz of possibilities. The power lies in its ability to collapse all that potential into a single high-probability answer that a classical computer can then verify. It explores the multiverse of answers to give us the best one from our own universe. So let's recap. Classical silicon is hitting a physical wall of heat and inefficiency. The von Neumann bottleneck makes our fastest chips waste most of their time waiting. Quantum computing bypasses these limits by using the strange rules of physics to compute in a massively parallel way, requiring entirely new cryogenic infrastructure. This is leading to a new model, quantum as a service, where access to these machines is rented via the cloud, making personal, high-end GPUs irrelevant for cutting-edge work. The value of traditional semiconductor stocks will be reassessed, while companies building ion trap and neutral atom quantum hardware will define the next era. We are at the beginning of the great silicon devaluation. By 2030, the NVIDIA GPU may be viewed with the same primitive nostalgia as a 1940s vacuum tube. We are not just on the cusp of a new technology. We are witnessing a fundamental shift in the architecture of intelligence itself. The story of computing is being rewritten, and we are only on the first page. If you found this deep dive into the future of computing insightful, make sure to like this video and subscribe for more technological breakdowns. What part of this quantum revolution surprised you the most? Let us know in the comments below.